Let's continue with our lecture on suspended growth reactors. In the last class, we have covered the mass balances of active biomass, soluble substrate, and debris for the biomass separator configuration. We also introduced active fraction and calculated the observed yield. In this class, we will see how these results can be utilized for reactor design. First, we can calculate the excess biomass production rate, as it is also how much biomass should be wasted from the reactor. We can substitute the total biomass concentration with the expression we deducted from soluble substrate and debris mass balances from the last class. Because the waste flow rate, Fw, times SRT divided by HRT is the influent flow rate, we can write expression for excess biomass production rate, whose unit is mass of TSS per time. We can see that the wastage rate, or the excess biomass production rate, is connected with the influent flow rate, the reduction of substrate concentration, yield, the stoichiometry and kinetics of decay, and SRT. Recall the expression for observed yield that we deducted from the last class. We can substitute it in the excess biomass production rate equation, and it circles back to the original definition of the excess biomass production, or biomass wastage, which is the overall growth of biomass and the generation of debris from the destruction of substrate. Besides the biomass wastage rate, we also need to know the oxygen needed to support the growth of aerobic biomass. We can write the oxygen consumption rate based on the stoichiometry and the kinetic matrix with COD parameters or TSS parameters. Recall the energy flow in biological reactions. The electron donor reacts with the electron acceptor, which is oxygen for aerobic processes, and generate energy for cell growth and maintenance. The ratio is determined by yield. For the decay process, electron acceptor reacts with active biomass to form debris. The ratio is determined by Fd. Therefore, the stoichiometry of oxygen supply is determined. The overall oxygen requirement in the reactor is the oxygen consumption rate times the reactor volume. We can expand the oxygen consumption expression. From previous deductions, we know that for biomass separator configuration, the growth rate can be expressed by 1 over SRT plus specific decay rate. And the active biomass concentration can be described by the mass balance of soluble substrate after substituting the growth rate expression. Finally, we can substitute the expression for active biomass concentration in the oxygen requirement equation to get this. Does it look familiar? Recall the expression for the observed yield. We can substitute to simplify the oxygen requirement equation to this. But what does it mean? We know that observed yield is the generation of total biomass divided by the consumption of substrate, considering decay and maintenance. So we can transform the expression of RO to this. It means the amount of oxygen consumed in the reactor equals to the total COD fed to the reactor minus the total COD coming out of the reactor. Also, nitrogen is required for cell synthesis. The nitrogen requirement is also determined stoichiometrically from biomass growth. In this empirical formula of biomass, the nitrogen content is 0.087 grams of nitrogen per gram of COD biomass. So the nitrogen requirement with a unit of gram of nitrogen required per gram of substrate COD removed is 0.087 times the observed yield times the TSS to COD conversion factor, as the observed yield is in TSS term. We know that the conversion factor typically has a value of 1.2 gram of COD per gram of TSS, so the value of nitrogen requirement is 0.1 times the observed yield. Because in CSTR, the influent is instantly diluted to the well-mixed reactor, the substrate concentration in the reactor equals to that in the effluent and is typically very low. Recall from the Monod equation, when the substrate concentration is low, we can approximate that the specific growth rate is first order of the substrate consumption rate. Can you think about what expression that we have covered is affected by this first order approximation? In all the mass balances, mu is actually expressed by SRT and the specific decay rate. So the first order approximation does not affect anything except the expression for soluble substrate concentration, which is derived from Monod equation. We have looked at the mass balance for the simple setup, one aerobic CSTR treating a single soluble organic substrate using a single type of biomass. In the next class, we will extend the model beyond that because in addition to just soluble substrate, the real-life influent may contain a wide variety of contents, such as inert particulate or soluble matter, biomass, and debris.